Welcome to CognitionChunks. This is DAGs, the directed acyclic side of order. Explaining order theory. Note this is coming from a relative novice on this topic, who is trying to learn about this topic from GPT. I am not a mathematician or an expert on this topic. A follow-up series to distinct types of math branches. Understanding order theory. Welcome to the intricate world of order theory. Today, we're diving into a realm where mathematics meets philosophy and has a love affair with computer science, economics, biology, and beyond. Sounds like a thriller, doesn't it? Well, in the scholarly world, it is. The building blocks. Order theory starts with some deceptively simple ideas. At its core, we have what we call a set. Think of it like a bag filled with individual, distinct items, like a bag of gemstones, each precious and unique. The other cornerstone is a relation, which is like an invisible thread that connects pairs of these gemstones in our bag. Let's talk order types. So how do these gemstones, or elements in our set, relate to each other? This brings us to partial order. Imagine a family reunion where everyone is related but not everyone talks to each other. That's like a partial order, certain gems are connected, but not all. Reflexive, think of it like self-love. Each gem is related to itself. Antisymmetric, imagine two people pointing at each other and saying, "We're equal." In our gemstone world, if two are related in such a way, they're actually the same gem. Transitive, this is like the friend of a friend principle. If one gemstone is related to a second, and that second one is related to a third, the first and third are connected as well. Move up the ladder, and we have total order, a kind of utopian society where everyone knows and is comparable to everyone else. In the world of gemstones, this is a situation where any two gems can be compared to decide which is greater. And then, there are lattices, those are like interactive communities within our bag of gemstones, where each pair of gemstones can figure out their common ground and how they can uplift each other. The marvels of math and theorems. In this universe of gemstones, we have fantastic phenomena like Zorn's lemma, a magical rule that assures us that if all connected groups of gemstones have a leader, then there has to be an ultimate leader of all gemstones in the set. And then there's the Naster-Tarski fixed-point theorem, think of it as social stability. If you have a function that preserves the order among the gemstones, that function will eventually find a gemstone that it cannot change. A pillar of the community, if you will. A universe of applications. This isn't just academic gymnastics. These concepts are the backbone of things like your computer's operating system or even the algorithms that determine what shows up on your social media feed. They play crucial roles in economics, helping understand consumer preferences, and in biology, helping decipher evolutionary relationships. The directed acyclic side of order theory. Now, imagine these gems are not just lying in a bag, but are part of a grand mural that is a directed acyclic graph or DAG. In this mural, every gem is connected with arrows pointing in certain directions, but here's the catch, no sequence of arrows will lead you back to the gem you started with. Mind-bending, right? If you've ever managed a complex project or created a to-do list for a month-long vacation, you've mentally created a DAG. These structures help us model dependencies between tasks, such as why you can't put up the walls of a house before laying its foundation. And if we go philosophical, DAGs make us ponder about causality. The arrows in a DAG are like the ripples of cause and effect, shaping our understanding of what leads to what without any chance of circular reasoning, which is crucial when it comes to debates about determinism and free will. Determinism and free will, philosophical and scientific perspectives. Speaking of which, let's talk about one of humanity's oldest debates, determinism versus free will. Imagine living in a world where every action you take, every decision you make, was already scripted. That's determinism. On the flip side is the intoxicating concept of free will, the power to act without the constraint of necessity or fate. In the realm of science, determinism was the darling child of classical physics. But then quantum mechanics walked in and said, well, it's not that simple. And neuroscience, don't get me started, suggests our brain makes decisions before we're even conscious of them. And why does this debate matter? Because it shapes our justice systems, our educational policies, and even the ethics of future technologies like artificial intelligence. So whether you're considering the complex relationships between elements in a set, modeling dependencies in a directed acyclic graph, or wrestling with the philosophical dilemmas of free will and determinism, remember, each of these topics isn't just an academic inquiry. They are ways to frame our understanding of the world, tools for problem solving, and catalysts for intellectual growth. And that's what makes diving deep into them so rewarding and enlightening. Join us again for another Cognition Chunks. Click the like button if you want more content. Was this accurate? Did GPT just make up a bunch of stuff that does not exist or does not make sense? Find out next time in the Cognition Chunks follow-up.